Hi everybody, welcome back. Today we're going to be talking about Kepler's laws, and we're going to finally talk about things moving in elliptical orbits. So far, we've only been talking about things moving perfectly in circles. So now we're going to talk about elliptical orbits, but mathematically it's not that big of a deal. But let's talk about this. Alright, so Kepler's 3 laws. So I'm going to briefly go over this, and then I'm going to go through each one. First one, and I'm just going to simply go over. You could go into a lot more, but I'm mostly just trying to cover what you need to know for AP Physics C. Each planet moves in an elliptical orbit with the sun at one focus of the ellipse. Okay, so I know that might sound a little confusing, but it's pretty much just saying all planets move in an elliptical orbit. So it's all of an ellipse, okay? It's not a perfect circle, which I think most of you guys know. Number 2, a planet and its sun sweeps out equal areas in equal times. Maybe that makes sense, but I'll explain that more later. Number 3, the period of a planet is proportional to 3/2 power of the semi-major axis. So the semi-major axis is pretty much from the middle point of the ellipse. This is what we call the semi-major axis, which is represented as this A. And I'm going to go through each of these laws a little bit more in detail. Okay, so the first one, Kepler's first law. Eccentricity is a dimensionless number from 0 to 1, which gives the shape of an ellipse. An orbit with an eccentricity of 0 will be a perfect circle. An orbit with an eccentricity of 1 is a straight line. The Earth's orbit has an eccentricity of 0.017, so it's very circular. I gotta change that. Okay, so one thing that we should know, let me keep reading. Perihelion is the point in the planet's orbit that is closest to the sun. Aphelion is the point in the planet's orbit that is the furthest from the sun. Semi-major axis is the distance from the center of an ellipse to the aphelion or perihelion. Okay, so depending on how is the eccentricity of an orbit, it shows how elliptical it is. So if something has an eccentricity of 0, that means that it's a perfect circle, okay? So that means that it's not elliptical at all, it's just a perfect circle. But 1 would be a perfect line. So it would just be a line going like this. It's a straight line, okay? So this just shows us how elliptical something is. It's going from 0 to 1, 1 being extreme elliptical, it's a line, 0 being extremely circle, perfect circle. Perihelion is the closest point from where it is to the sun, and aphelion is the furthest point from where it is to the sun. Okay? And the semi-major axis is just pretty much how far it is from the middle point of this orbit. Okay? This A. Okay, so those are things to know. Okay, moving on. Kepler's second law. Okay, a lot going on here. Don't get overwhelmed. The further the point is to the sun, the slower it will travel. The closer the planet is to the sun, the faster it will travel. The area a planet sweeps out equals the area sweeps out equal areas in equal times. So one thing that we should know is the further out the planet is, if this is Earth here, then that means it's going to be slower. And that should make sense because the force of gravity will be weaker, so it won't be moving as fast. What we can tell is over here, like in January, the planet will be moving a lot faster because it's closer to the sun, meaning the force of gravity would be a lot stronger. Okay? But what this second law is telling us is the area planet sweeps out equal areas in equal time. So from June to July, the planet moves from here to here, that we can see. But from December to January, we see that it moves a lot further distance. And that's because it's going a lot faster from December to January compared to June, July. However, the area under the curve, if you were able to calculate that using some calculus, what would happen is we would see that this area under the curve would still be the same. So every month, as you can see here from July to August, August to September, September to October, the planet's always going to be going at a different speed, but the area under the curve, within the given time period, is pretty much going to be the same. So it's like, a month varies, so I guess it'll be slightly different. But the area on the curve is pretty much going to be the same, with equal time. Okay, I hope that makes sense. You won't really see problems like that, but it's good to know conceptually. The last one, Kepler's third law. Even though planets orbit in ellipses, a lot of the calculations can be made just as if the orbit was in a perfect circle, with the semi-major axis equal to the radius. The calculations work out like this because the planet at times moves very quickly and other times slowly. So we know as this planet is going around in an ellipse like this, further out here, it will be going slow. Slow, yep. And the closer it gets to the sun, the faster it's going to go. So even though it moves in an ellipse, we can pretty much just treat it as a perfect circle when we're looking for how long it takes. So what we're going to do is we're going to treat this semi-major axis A as the radius. And because the speed varies, it pretty much just equals out as if it was moving in a perfect circle where the A equals the radius. And that's how we get this equation here. We have this equation, force of gravity equals G, mass of planet, mass of sun, divided by R squared. But we can just say that's the semi-major axis. Things cancel out. Then we know that velocity is equal to 2 pi over t, 2 pi r over t. So we substitute that in, all squaring everything. And then we can derive and get this equation here. It's important to either memorize this equation because it's not on your formula sheet, or be able to derive it quickly because it comes up a lot in this chapter. Okay? All right, let's start doing some example problems with this. Oops. Okay, example number 15. Pallas, which is, an asteroid, has an orbital period of 4.6 years and an orbital eccentricity of 0.233. What is the semi-major axis of its orbit? Okay, so let's look at this. We're trying to find this semi-major axis, which is this A value here. So I'm just going to derive everything. Well, maybe first let me change this 4.6 years into seconds. So I can see that the period is 4.6 years. I'm going to get this in a second. So I'm going to multiply this by 365 days, multiply that by 24 hours, multiply this by 60 minutes, and then multiply by 60 seconds. So I could get this answer in seconds. Give me a second while I do that. 4.6 times 365 times 24 times 60 times 60. And we get around a big number that I'll need to write down first before I can say. 65600. Okay, so let's see. 145,065,600 seconds. Okay. So now let's see, what are we looking for? The semi-major axis. Okay, so force of gravity equals G, mass of Pallas, mass of sun, divided by R squared. We should know this force of gravity, we can change it to be the force centripetal, because the force of gravity is what's allowing it to go in a circle. So I'm going to change this to the mass of Pallas, velocity squared divided by r. One of the masses cancel out. One of the radius cancels out. And then we have velocity squared, which we can again change to be 2 pi r over t. So 4 pi squared r squared is equal to g, mass of sun, divided by r. And I'm going to bring this r to the other side. So I'm going to bring this r over here and change this squared to a cubed. Oh, whoops, I forgot the t. Let me put the t here. So t squared. So let me try to isolate this r. So I'm going to put r cubed is equal to g mass of sun, t squared, bringing this t to the other side, and bringing this 4 pi squared to the bottom. 4 pi squared. Okay, so from here, let's start plugging all this in. R cubed is equal to G, which is 6.67 times 10 to the negative 11. Mass of the sun, which is 1.99 times 10 to the power of 30. T squared, which is going to give us this 1.45 times 10 to the 8th. And this is also squared. We have this t squared there. All divided by 4 pi squared. And then if we want to get rid of this cube, I'm going to just divide this by the power of 1/3. Okay, so give me some time as I put this all into my calculator because this is going to take a while. 10 to the power of 8 squared times 1.99 times 10 to the power of 30 times 6.67 times 10 to the power of negative 11 divided by 4 pi squared. Put all of that to the power of 1/3. And what we should get is the radius is equal to 4.13 times 10 to the 11 meters. Okay? And that's what the radius is equal to, but we should also know that this is the same as the semi-major axis, okay? Because mathematically, it's going to be the same thing. So the semi-major axis is equal to this 4.13 times 10 to the 11 meters. And what we should also know is that the eccentricity doesn't matter. Okay, so mathematically speaking, we can treat this as a perfect circle and it'll give us the same answer. Okay, let's move on. All right, this next problem is pretty difficult, but this is the last one. It's not difficult, there's a lot just going on here. All right, so let's look at this. Comet Halley moves in an ellipse around the sun. It has a perihelion distance of 8.75 times 10 to the 10 meter and an aphelion distance of 5.26 times 10 to the 12 meters. The sun that it orbits has a mass of 1.99 times 10 to the 30 kilograms. That's our sun. Find what the semi-major axis is. Okay, so first off, we're trying to find the semi-major axis, which is pretty much this length right here. I'm going to call this A. Let me draw that a little better, but that's what we're looking for. This A value. Okay. How I'm going to find this is I know the length of perihelion and I know the length of aphelion. So I'm going to add those two together and then I'm going to divide by 2. So the semi-major axis is equal to, 8.75 times 10 to the 10 plus 5.26 times 10 to the 12. And then I'm going to divide this by 2. And then this is going to give me the answer right here. So let me put that in. 8.75 times 10 to the power of 10 plus 5.26 times 10 to the power of 12. Divide this by 2. And then what I get is 2.67 times 10 to the power of 12 meters. Okay? And what this is telling me is that from the midpoint, this length here is 2.67 times 10 to the 12 meters. Now, part B is asking for what is the eccentricity of the ellipse. So we want to know how elliptical is this. Is this kind of like a circle or is this more of a line? We want to know how this is. And what I want to do is I want you guys to look at this picture over here. We know that this length from here to here is equal to EA. So what that's showing us is from here to here is EA. Okay, we know what A is. That's given to us, 2.67 times 10 to the 12. Now we have to find the E. How we're going to do that is we know the distance of the perihelion. The distance of the perihelion is equal to 8.75 times 10 to the 10. So we're going to subtract these two to get EA. So part B. EA is equal to the semi-major axis, which is 2.67 times 10 to the power 12, minus this perihelion distance, which is 8.75 times 10 to the power 10. And then what we get is we get EA is equal to, let me put this into my calculator, minus 8.75 times 10 to the power 10. We get this as 2.586 times 10 to the power of 12. And then I'm going to change this EA to be E, and then A being 2.67 times 10 to the power of 12. So I'm going to divide this by 2.67 times 10 to the power of 12. And then what I get is the eccentricity. Ooh, let me put it over here. The eccentricity is equal to 0.9 969. Okay, so we can see that it is very elliptical. It's almost like a straight line. Okay, Comet Halley is very elliptical. Okay, part C. So part C is asking for what is the period of Comet Halley. So we want to know how long does it take for Comet Halley to come to the sun. So I know, like, I think it visited like 30 years ago. So anyway, and I think it's going to be like another 40 years until it comes to Earth again. So anyway, that's a fun fact. But we're trying to find this period. So this is similar to what we did last time. We could either have memorized that equation or we can derive it. I'm just going to derive it, but I'm going to do it quickly. Force of gravity is G, mass of Halley, mass of sun, R squared. This force of gravity changes to be mass of Halley, V squared. Mass of Halley cancels out. And then I'm going to, whoops, I forgot the R. One of the R's cancel out. And then I'm going to change this velocity to be 4 pi squared, R squared, divided by T squared is equal to G, mass of sun, over R. And then I'm going to bring this R to the other side to make it R cubed. And now let's see if I can find what the period is. So I'm going to say, I'm going to bring the period to the other side. So this is going to be 4 pi squared. And the R, remember this R is the same as the semi-major axis. So I'm going to put 2.67 times 10 to the power of 12. This is cubed, divided by the G, which is 6.67 times 10 to the negative 11, times the mass of the sun, which is 1.99, times 10 to the power of 30. And this all equals T squared. Okay. So let's figure out what this period is. Give me a second, because again, this is going to take me a little while because we have a lot of big numbers here. I don't want to mess up while I'm talking. 3 divided by 467 times 10 to the power of negative 11, 1.99 times 10 to the power of 30. And what we should get is we get a period of 2, 3, 7, 9, 3, 4, 4, 3, 8, 0 seconds. Or, let me just do this into years. Divided by 60, 24. And we should get 75.45 years. Okay, so it goes around the sun. But this period is equal to this big number. I should set my calculator differently so I could have it in scientific notations. Or 75.5 years. Okay. All right. Now part D. So part D, this might be a little bit tricky, but part D says Comet Halley travels 910 meters per second at the aphelion. How fast will it be traveling at the perihelion? Okay, so let's look at this. We want to know how fast it's going to be traveling at the closest point, and we know how fast it's traveling at the furthest point. So at the furthest point over here, it's going 910 meters per second. And we want to know how fast it's going at the furthest point. Okay, we want to know what the speed is here, or the closest point. Okay, so this is important. This comes up once in a while. But what we should know is the angular momentum at one point equals the angular momentum at another point. Because the torque is equal to 0, angular momentum is conserved. Okay, angular momentum is conserved. So even though the inertia of this will change as it gets further away from the sun and it gets lower, or I should say it increases, the omega, how fast it's going rotationally, is going to decrease. So as it gets closer, the speed increases, but the radius decreases. As it gets further, the radius increases, but the speed decreases. So we can treat this as a particle, this planet or this Comet Halley. And we could say that this M1 B1 R1 is equal to M2 B2 R2. And let's call the beginning part, we'll call that the aphelion, because that's the stuff we know at the beginning. And the final part, we'll call that the perihelion. Okay, so the mass of comet Halley, we don't know what that is. We do know at aphelion it's going 910 meters per second. And we do know how far it is. That's going to be 5.26 times 10 to the power of 12. And this will be equal to the mass of the comet Halley, which we don't know. The velocity, which we don't know, that's what we're looking for. And the radius, which is given to us, 8.75 times 10 to the power of 10. So even though we don't know the mass of the comet, we see is they cancel out. And then we can see what the velocity is at the furthest point. 910 times 5.26 times 10 to the power of 12 divided by 8.75 times 10 to the power. And then we should see it's going a lot faster at the furthest point, 54,704 meters per second. Alright guys, and that's all we're going to be covering for today. I hope all that made sense, and I'll see you in the last video where we do some advanced problems. Thanks for watching, everyone.